Our next speaker is Dr. Jay Johnson. Dr. Johnson is an associate professor of animal welfare and stress physiology in the Division of Animal Sciences at the University of Missouri. The overall goal of his research program is to identify production-relevant stressors and evaluate and mitigate their impacts on livestock health, productivity, and welfare. Dr. Johnson's research program uses an integrative physiology approach encompassing aspects of stress physiology, nutritional physiology, and applied ethology to develop and/or improve upon livestock husbandry practices that enhance animal health and welfare while maintaining or increasing economic return for producers. Specific research areas include improving heat stress resilience in swine through genomic selection, improved management and nutrition to reduce the negative effects of pre- and postnatal heat stress, and mitigating the effects of early life stressors on gastrointestinal function in swine to improve health, performance, and welfare metrics. Dr. Johnson will present on heat stress in sows, the impacts and strategies for improving production and welfare.
Well, thank you very much for that introduction, and thanks to the committee for inviting me to speak today. I'm pretty happy that I'm going last here this morning. I think Drs. Bortolozzo and Nauer actually set me up really nicely for this presentation, and I'm going to be talking about how we're managing our gestating and lactating sows, more from a research perspective and what we're seeing in the lab. And so before I get into that, I just want to talk a little bit about how we've advanced over the years in terms of our pork production, right? We know that global pork production has increased fourfold in the last 50 years, and this is primarily due to a rising demand for meat products, as well as our improved technologies, right? We're producing an animal that's growing faster, has more lean meat, we're feeding that animal better, and we're putting that animal in a better housing strategy, right? And so this is a photo. Maybe you might have seen a farm about 60 to 70 years ago, looks like this. Perhaps in certain parts of the world, we may still see this. And then this is where we've come to today. And we know that production needs are going to continue to increase, and again, because of that rising global population and demand for a high quality protein. And so with these advancements, we've seen increases in things like litter size, growth, disease resilience, meat quality and quantity, and we've also seen some really nice improvements in the welfare of the animals that we're raising. But like with anything, with the good often comes some poor consequences. With this increasing growth rate, we've seen an increase in metabolic heat production in our modern pigs. There's a really nice paper out of the ARS from Dr. Tammy Brown-Brandel about 10 years ago, where she looked at metabolic heat production in our lactating and gestating sows. And she compared that against pigs from back in 1956. And what she'd found was that our modern pig, at least 10 years ago, had about a 133% increase in metabolic heat production. We're also gaining a greater understanding that production stage and physiological state can also impact the sensitivity of our animals. And so when we're setting those ventilation settings, it's really going to be important to understand what stage in that production process your animal is and set it appropriately to meet the thermal needs of that animal, right? For instance, we know that gestating and lactating sows are much more sensitive to heat stress than our non-pregnant or open animals. And so when these animals are exposed to high ambient temperatures, they go through a variety of different biological processes to deal with that stress. And unfortunately, because that animal is trying to maximize its own survival, we're seeing a drop in our production outcomes. And so with heat stress, we'll commonly see, right, decreases in lean muscle growth, lactation performance, poor animal welfare, and some of the larger economic issues that we see are decreases in things like reproductive issues for our sows, as well as that summer-induced mortality due to heat stress. This is a nice figure that Bradley Eckberg from MetaFarms had recently published, where he demonstrates we see this large increase in mortality in our sows during that June, July, August times here in America. And so with that, I know Mark had talked a little bit about economic impact, two papers that are very widely cited in the heat stress literature. Dr. St. Pierre back in 2003 estimated about $300 million in losses, whereas Dr. Pullman estimated about $55 in losses due to sow reproductive issues. If we extrapolate that to today's dollars, that'd be about $511 million today adjusted for inflation, or about $79 per sow that we may be losing due to heat stress. What's important to note, though, is just extrapolating for inflation, we're not including the negative impacts of things like in utero heat stress on future performance of those pigs, as well as an increasing incidence and frequency of these heat stress events that we're seeing due to climate change. And so touching a little bit on in utero heat stress, this is an area of research we've been focused on for probably about the last 13 to 14 years. And in every instance, we've observed that in utero heat stress in those piglets is associated with negative economically relevant postnatal phenotypes. We see the effects of in utero heat stress applied on that pig throughout its entire life, regardless of the temperature that it's exposed to later on. And we've seen that the first half of gestation is actually more likely to cause an animal to suffer from in utero heat stress related phenotypic issues. Primary risk factor for in utero heat stress is either a chronic and low increase in maternal body temperature or an acute and very high increase. And what we see in those piglets is alterations in things like immune function. They actually become more hypersensitive to immune challenges. We see greater pro-inflammatory cytokine production and inflammation. We see differences in how they respond to stress, differences in meat quality and quantity, so both reduced quantity and decreased quality of that meat. And of course, a very classic decrease in growth performance from both a gain standpoint and a feed efficiency standpoint. But I want to focus a little bit more about the direct impacts on that gestating and lactating sow. And so my background is actually in nutritional physiology, and I've combined that with some of our stress physiology. And so we're really interested in how bioenergetics of that animal can be influenced by heat stress, especially in terms of nutrient availability and how we're feeding those animals. And so very classically, we really associate a lot of our production losses in our pigs and other livestock species with that decrease in feed intake, right? And so animals will naturally decrease feed intake under heat stress because they're trying to deal with that metabolic heat production to balance heat gain with heat loss. So we know that the more that animal eats, you may think, here in North America, if you go to a Thanksgiving meal, you eat a lot of food, you feel really warm afterwards. It's the same thing that's happening to a pig, right? So it wants to decrease in feed intake to decrease heat production to deal with that challenge. There's also been reports that heat stress itself can actually increase the basal metabolic rate of our animals by increasing maintenance costs. And this may also have a negative impact on their ability to grow and produce milk. And then more recent work, Iowa State University and others have shown that there's altered post-absorptive metabolism that occurs. So different priorities in how that animal is partitioning those nutrients into either meat or milk. And so again, when we think about feed intake and productivity, we know that there's reduced energy consumption during heat stress to decrease that thermic effect of feeding. And again, that animal is trying to balance that heat gain with that heat loss. And so very classic example, we see that our ad libitum fed heat stress grow finish animals will generally see a decrease in feed intake. In this particular study, we saw about a 13% decrease in feed intake. And with that, we saw about a 12% reduction in average daily gain. And this is pretty commonly seen throughout the industry and in many research trials. But is this always true? Do we always get a decrease in growth rate under heat stress conditions? Well, I think it depends. So when we think about our gestating animal, we know in practice, we limit feed these animals, right? And so we feed them to what we determine as maintenance costs. However, when you actually look at these gilts, when they're exposed to heat stress or thermoneutral conditions, if we're capping their feed intake, in this case, no difference in feed intake because we've limit fed them, we actually see that our heat stress gilts will outperform our thermoneutral gilts. So in this case, our gilts that were exposed to heat stress from day 0 to 33 of gestation grew about 72% faster, and they were about 69% more feed efficient than our thermoneutral animals. We see the same results in our multiparous sows. In this case, we exposed them to heat stress for that first half of gestation, 0 to 60. Again, no difference in feed intake, but we're getting about a 28% increase in average daily gain for these multiparous sows, and about a 29% increase in feed efficiency. So the feed energy that they're consuming, they're utilizing more efficiently and growing faster. So why do we get this discrepancy between an ad libitum fed and a limit fed animal in our production systems? Well, we really think it comes down to maintenance costs and how are we calculating this, right? So again, early reports indicate that maintenance costs increased during heat stress. This is reported in many different species, not only pigs, so in cattle, sheep, rodents, and again in pigs, we've reported that maintenance costs are greater. And this is generally attributed to those greater energy costs for our heat mitigating processes, right? So when that animal's respiration rate goes up, that costs energy, and this has been attributed to causing that increase in maintenance costs. But is this actually true, right? So can we actually measure maintenance costs in our heat-stressed animals? And so there's a couple different ways as researchers that we use to look at energy balance and maintenance costs in our animals. The gold standard for this is indirect calorimetry, right? And so we use fasting heat production as an indicator of those maintenance costs. The problem with using this method with a heat-stressed animal is that in order to determine fasting heat production, we need to take away feed, right? And if we take away feed from an animal, you're going to decrease its heat gain, and you make that animal more heat tolerant, right? It plays a huge role in the body temperature of that animal. And so we've determined that it's really not a suitable method for determining maintenance costs in our heat-stressed pigs because we don't know if those maintenance costs have changed because that animal just became more tolerant to the heat stress that we're applying to it. Another method that we may be able to use is the comparative slaughter technique, right? And so in this technique, we're actually taking the animal, we're grinding the entire carcass, and we're looking at the amount of protein gained and lipid gained over a certain time period when that animal is exposed to certain environmental conditions. And so with this methodology, those pigs can remain on full feed, so we're not altering their heat tolerance due to taking the feed away, meaning that there's no experimental influence on that heat tolerance of the animal. And so back in 2015, when I was at Iowa State, we actually did this. And so we looked at how does heat stress influence maintenance costs in our growing finishing animals. Using this method, what we found was that maintenance costs were decreased in our heat-stressed ad libitum fed grow-finish animals. During that growing phase, we had about a 588 kcal per day reduction in maintenance costs. And during that finishing phase, it was about a 433 kcal per day decrease. And so when we think about energy partitioning between an ad libitum fed on the left and a limit fed animal, it really comes down to what is that net increase or decrease in energy available for growth. If you allow an animal to just consume as much feed as it wants to, naturally we're going to see a decrease in total feed intake or gross energy intake for our ad libitum fed animals. So regardless of how much heat stress is decreasing maintenance costs, you're going to have a net decrease in energy available for growth, right? And that's why we see those decreases in gain. But if you cap their feed intake, like we do with our gestating animals, then that's when that maintenance cost decrease really allows for that net increase in growth, energy for growth. And I think that's why we're seeing this increase in growth in our limit-fed gestating animals. So the next question is, if these animals are at a more positive energy balance, where are those nutrients actually being partitioned to? Are they being partitioned to a place that's going to be beneficial for that animal's ability to produce? And so in this study, we were interested in whether or not, and again, these are the same group of animals I showed you earlier that were growing faster, if we were getting impacts on fetal development or the number of fetuses. So maybe additional energy was being partitioned towards reproduction. What we found, though, was the exact opposite. We found that the total fetuses in those animals were decreased by about 17%. This kind of goes along with Dr. Nauer's research showing that, litter size differences. We also find that the number of viable fetuses in those gilts were decreased by about 15%. And when we looked at fetal weight, there was no difference, right? So this animal is not partitioning that excess energy towards reproductive processes. So the next thing we wanted to look at is mammary development. So maybe these additional nutrients are actually going to go towards supporting future lactation for this sow or this gilt. Unfortunately, that wasn't true either. So what we found was that if we'd exposed animals to heat stress in that early part of gestation, and then we didn't expose them later, we found the sustained impact on mammary gland development in our replacement gilts. And so we see a decrease in mammary cell proliferation, and so which is a bioindicator of that animal's ability to actually produce milk in that first, second, third lactation. And so these animals don't appear to recover from those early gestation insults, particularly when you're exposing our replacement gilts to heat stress in that first half. And we have some ongoing collaborations right now to further expand on this research, looking at things like colostrum and milk quality with Dr. Farmer. So what it really appears is that those animals are just keeping those nutrients for themselves, right? They're not going into those reproductive and lactation outputs. What we see is that those sows and gilts are putting on about 354% more back fat, right? So they just keep that extra energy for themselves. And so we may need to rethink a little bit about what are calculated maintenance costs based on different heat stress thresholds, and do we need to think about feeding animals a little bit differently depending on the temperature they're exposed to? So we see that animals are in that more positive energy balance, right, when we limit feed them under heat stress, but does this translate to lactation? And so as we started to think about this process, we really looked to the dairy cattle literature because they've done a lot more in this area on the direct effects of heat stress on lactation output. And so I looked at some work by Dr. Harold Johnson, who was from the university. He was one of my predecessors at the University of Missouri doing very similar research. And so at the University of Missouri, back in the day, in the 40s, 50s, 60s, 70s, we published a lot of work as the Missouri Agriculture Experimental Station. So much of this work was never actually published, but at the University of Missouri, we have this giant cabinet with these articles that go all the way back to the 40s when Sam Brody was there. And I found this research bulletin by Dr. Johnson where they had force-fed heat-stressed lactating dairy cattle via a rumen fistula to that same level as the thermoneutral dairy cattle, right? So they let thermoneutral dairy cattle consume as much feed as they want, and then they exposed another group to heat stress and basically forced them to consume through that fistula as much feed as those thermoneutral ones were, right? Putting them at the same plane in nutrition. I'll note though that this experiment had pretty low experimental power, right? 2 cows per treatment, but I think it's pretty interesting nonetheless. So what Dr. Johnson found was that very similar to our gestating pigs, when he force feeds these dairy cows to the same level as thermoneutral ad libitum animals, they actually grow faster than if you have an animal that's ad libitum under heat stress, right? So you're providing them more energy, they're growing faster, and they're also growing faster than our ad libitum thermoneutral animals too, right, to which they're being compared to. So we're seeing this increase in growth indicative of more positive energy balance. However, when he looked at milk production, he found that it wasn't fully rescued, right? And so as expected, the ad libitum heat stress animals had about a 12.6 pound per day reduction in milk output. When you force feed your heat stress animals to thermoneutral levels, they still are at about a 5 pound per day deficit compared to your thermoneutral animals that are at the same plane in nutrition. And so this additional energy available is not being allocated into milk at all. And essentially, only 60% of that milk production loss was due to feed intake alone. The other 40% was due to the direct effects of heat stress. But again, is this enough cows to really draw conclusions and hang your hat on? So about 43 years later, Dr. Lance Baumgard did a study when he was at the University of Arizona, where he basically repeated this using a pair-fed model. In this study, he had a little bit better power. He had 6 cows per treatment, and he had a thermoneutral group that was fed ad libitum, a heat stress group that could eat as much as they wanted, and then a heat stress group that they fed to and then a thermoneutral group that they fed to the same level as the heat stress animals. What Dr. Baumgard found was very similar to what Dr. Johnson had found 43 years ago, that only 50% of milk production losses are due to feed intake, right? And so the direct effect of heat stress has a large impact on that animal's ability to produce milk. So is there a similar response in pigs, right? Can we learn from the dairy cattle researchers and apply this to our lactating sow? So this is a paper back in 1998 from the INRA group in France, where they did a very similar study, right? They had a thermoneutral group that ate as much as they wanted, and then they had one that was restricted to the level of heat stress, and then an ad libitum heat stress. And what they were using was litter growth rate as an indirect indicator of milk output by the sow. And similar to the dairy cattle work, they found that if an animal was fed ad libitum under heat stress, those piglets were still growing slower than restrict feeding a thermoneutral animal, right? So in indicating that despite the similarities in nutrition, the heat stress is having a direct impact on that sow's ability to produce milk. But what about some direct sow-based evidence on the impacts of milk production? And so one of the reasons why we don't have a lot of research on total milk output is it's really hard to measure milk production in the sow, right? Very logistically difficult, labor intensive. We need to remove the piglets and we need to handle the sows, which could also impact milk production. And generally we have to administer oxytocin to promote that milk letdown. There are methods out there that people have used, things like the weigh-suck-away method, hand expression or modified pump system. But again, it's still pretty difficult to accurately measure total milk output on that 21 or so day lactation period from a research perspective. And so our group has actually been using indirect calorimetry to get an indirect indicator of how much milk that animal is producing. And so again, as I talked about earlier, we can use this to estimate heat production and measure total energy balance in our animals. And we know that total metabolic heat production is pretty closely related to total milk production in sows. A nice paper by John Black in 1993 estimated that a 20% decline in total heat production in our sows equated to about a 25% decline in total milk production. One of the issues is many systems designed for a lactating sow are going to measure it at a room level as opposed to an individual animal level. And so it's really hard to differentiate sow-to-sow variability with these systems. And so my group, we developed to deal with this issue our individual sow indirect calorimeters, right? And so we call them our pig bubbles. We essentially put a sow in a crate inside a large pan of water, and we put this polyethylene plastic down around the side of them and turn it into a positive pressure system so we can measure metabolic heat production, right? We're also able to separate the sow from the litter, and so we'll take sentinel piglets and we'll measure their metabolic heat production and apply that as a correction factor to see what is the sow level total heat production and then what is the litter plus sow level total heat production. And so what's the application here? And so we performed a study with Drs. Alan Schinkel, Bob Stwally, and Francisco Cabezon to look and see how their electronic cooling pads would impact milk production in our sows, right? Using metabolic heat production as that indirect indicator. What we found, like we've generally found with this, is that we were able to keep those sows cooler with that cooling pad. We got about a 25 breath per minute decrease in their respiration rate and about a 0.4 degrees Celsius decrease in vaginal temperature in these sows when we gave them their cooling pads. Unfortunately, though, in this study, we didn't cool them quite enough to rescue feed intake for those sows. And so we essentially developed what I'll call a poor man's pair feeding model with this study. So there's no difference in feed intake, but the cooled sows are cooler than our heat stress sows. We then looked at total metabolic heat production as an indirect indicator of milk production. And interestingly, what we found is that despite the fact these animals were at the same plane in nutrition, our cooled sows were producing about 20.4% more metabolic heat. And again, going back to that paper by Dr. Black, a 20% decrease in heat production, he believed was equated to about a 25% decrease in milk production. When we look at the performance of those piglets then, we found that our piglets from the sows on the cooling pads that had that 20% increase were growing about 25% faster. So it looks like Dr. Black was at least pretty much right, I think. We also found that piglet weaning weight was increased by about 19%. So even though those heat-stressed sows or those cooled sows are at the same plane of nutrition, they're still outperforming our heat-stressed sows simply due to the fact that we're cooling them. And so some potential industry implications from this. We're interested in whether increasing feed intake during heat stress may not actually completely rescue lost sow lactation performance, right? I think that's kind of the dogma that we go with, just get more feed in her, she'll produce more milk and better piglets. From an experimental standpoint, we're not really seeing that. So we think there's some direct biological effects of heat stress on that lactating sow performance, likely similar biological mechanisms as we see in our dairy cattle. And so we think that cooling strategies really need to be used proactively to help rescue that lost lactation performance, and that feed intake alone may not necessarily cause improved lactation under heat stress, or at least an improvement to the level that we'd like to see under thermoneutral conditions. And so saying that, what are some options that we currently have to cool our lactating sows or our gestating sows, right? And so we use these cooling technologies, and they're really the first line of defense against some of these heat stress related issues, right? There was a really nice session yesterday on ventilation systems. Can we increase ventilation in that facility to pull heat out and keep those animals cool? Evaporative cooling pads, again, Dr. Nauer talked about the importance of making sure those are working correctly. You got water throughout the entire evaporative cooling pad. Drip coolers, and then of course conductive cooling pads that I talked about earlier are very effective in keeping that animal cool. And then of course just providing cool water. But one of the questions that we see, and one of the things that we've noticed talking with producers, is that there may be a lack of understanding, or at least updated understanding of what sort of guidelines do we need to actually apply these technologies, right? Are we either over-applying them or perhaps under-applying them and not applying them at the right time? So Drs. Kara Stewart and I, we conducted a survey, and we received responses from about 97 swine farm managers in the US across 17 states. They manage pigs, range from about 3,000 to 120,000. And one of the questions we asked them was very simple. When do they think heat stress occurs? Okay? And so we asked them for a variety of different pig categories. So our nursery, grow finish, market pigs, mature boars, and our sows. Okay? What was very surprising to us was the range in responses we received from these producers, right? We're getting a standard deviation between about 3 to almost 6 degrees Celsius, right? We had some producers that responded that told us, well, we started about 75 degrees. We had others that told us 90 degrees Fahrenheit, right? I mean, it's a huge range. And so we can develop as many technologies as we want, but if we're not providing proper education on when to use them, those technologies are not going to do us any good. What's also interesting about this, we compared the average responses of these producers to our current guidelines, again, are about 30 to 40 years old. And these thresholds we were given on average were about 2 to 4 degrees Celsius greater than even those 30 to 40-year-old recommendations, right? And so I think there needs to be more education on when we need to start applying these technologies. And so another question we ask is, what's currently available for producers to use, right? What are the newest scientific recommendations that are out there? And so there's primarily 3 that we identify. The first being the Livestock Hot Weather Safety Index. You may see this in some training tools on how to deal with pigs. But I will mention that this index was actually developed for cattle, back in 1970. It was not developed for pigs. And obviously a cow deals with heat stress a lot differently than a pig does. It's much bigger. And so I think it's a little bit, I'd be interested to see in what are the pig's actual response to using these indices. We also use the temperature humidity index, but again, this was developed for humans back in 1959. Humans sweat, pigs don't. So humidity plays a much greater role even at lower temperatures in a human than it does in a pig. There's more recent ones that are more specific to pigs. In this case, the temperature humidity stress index for growing finishing swine. Again, this was developed in 1998, which is about 26 years ago, and we know that our modern pig produces a lot more metabolic heat than it did 25 years ago. Plus, it's not specific to sows. And so we wanted to see if we could develop an updated and sow-specific option. And so in doing this, we wanted to look at both behavioral thermoregulation, so where does that animal want to be at, as well as that animal's physiological heat stress response. So we performed a variety of studies, and I'll focus mostly on our sow work, where we actually developed what we call a thermocline. So it's a large chamber that ranges from 10 degrees Celsius, or about 50 degrees Fahrenheit, all the way up to 35 degrees Celsius, or 95 degrees Fahrenheit. We put these animals in there and we video record them over a period of time, and we identify which portion of that chamber are they spending most of their time. And we develop our cubic regression models to identify when is that peak temperature, and then what is that range based on 2 standard deviations from the mean. What we found with our system is that our late gestation sows prefer to be at a temperature of about 14 degrees Celsius and at a range from about 12.6 to 15.6 degrees Celsius. That's where they spend the most of their time in our systems. Whereas our non-pregnant mid-gestation animals, they'd really like to be at about 13.2 to 16.4 degrees Celsius, or 56 to 62. That's where they spend a lot of their time. And so using this behavioral data, we're able to identify when that animal may be cool, right? So anything under that thermal preference range, where it may be most comfortable, so anything within that thermal preference range, and then where they may be starting to get warm, right? So anything above the thermal preference range, but below the start of actual mild heat stress is how we define that in our algorithms. We also look at sow physiological heat stress response. And so with this, we're able to define mild heat stress, moderate heat stress, and severe heat stress. And I forgot to change that title, so ignore that. But what we saw was that respiration rate was a really nice indicator of mild heat stress, right? This is the point at which active heat loss attempts begin by that animal. And so we're looking at the inflection point of respiration rate as a function of temperature. Moderate heat stress is the point at which body temperature rises, and then severe heat stress is when body temperature starts to rise uncontrollably for that animal, which is the classic definition of upper critical temperature threshold. Using this information, we're able to derive a decision support tool with algorithms specific for our non-pregnant or early gestation, our mid-gestation, or our late gestation animals. But again, I don't expect a producer to go out and plug in temperature and humidity into all these equations, right? It's just too difficult to do. They have more important things to do. And so to try to improve usability for swine producers, we went ahead and we incorporated these algorithms into our free smartphone app, which we call Hot Hog. It's freely available on the Apple App Store and Google Play. I know some organizations are currently using it as an outreach tool. I just spoke with one of my collaborators in Australia, and I know that Australian Pork Limited is currently using it for outreach. We've targeted mostly towards swine producers, but we also think that researchers may have benefit from this. As we start to have more interest in heat stress research, can we really standardize those protocols that we're using for our animals so we don't get so many variable results across research projects? And within the app, it does provide real-time information on thermal stress risk. You can customize your own risk threshold. We've recently added alerts, so you don't have to constantly look at the app. And then it's available in 4 different languages, including English, Spanish, Brazilian Portuguese, and Chinese. For those of you that don't like apps, right, we also have developed heat maps out of this. And so these are things that could be provided. You can put them on a poster up in your barn. Just give your employees a better idea of when they need to start considering heat stress for your gestating sows at different stages. Just going through the app itself, it'll give you your current thermal index. You can select your gestation stage depending on your interests. It'll give you thermal index hourly predictions with a scrolling bar. It also gives you that thermal index weekly predictions. And you can also get your weather data from the same app, so you don't have to go back and forth between your weather app and your Hot Hog app. You can set specific locations, and so if you have maybe barns in several different states or even parts of the world, you can set it based on latitude and longitude, as well as name of the city. And there's also support for management decisions, and so our in-barn management was designed with consultation from several major swine industry partners here in the US. And then we developed our transportation guidelines through the TQA process in collaboration with the National Park Board. And again, if you're trying to set your ventilation settings, we also have an option to build your own thermal index. And so you can type in different temperature and humidity combinations, and it'll let you know if that animal is or is not going to succumb to heat stress. And this may be an important tool for identifying where you need to set your ventilation settings at. We do have some future updates planned, currently trying to work on developing new thermal indices for our nursery, grow, finish, and market pigs, which will be additional tabs here within the app, using that same development pipeline. But again, we think that really updates are probably required in at least 10 to 15 year intervals in order to maintain accuracy and keep up with our genetic progress as our animals are more efficient and more productive. But again, we can do all this from a research standpoint, but really producer education and training is very key. People like Mark and other extension folks, working with us to try to get this information out to our producers. And so some take-home messages. We know heat stress has many negative effects on swine performance, health, and welfare. I think, and I think others think, that the economic costs of heat stress are probably greater than we currently assume. We haven't accounted for things like in utero heat stress, climate change, and the increased heat stress sensitivity of our modern pigs. And so improving environmental management, using validated decision support tools, and incorporating employee training, I believe could be beneficial for improving that heat stress resilience and industry profitability. With that, I want to acknowledge all the students that were involved in the research over the years, as well as our funding, and I will entertain any questions. I think I went a little over time, but luckily I'm last, so.
Great work, Dr. J. Johnson. I got a little confused when if you, let's say you don't have much capabilities to cool down those sows during the summer. How much of an impact can you expect if you concentrate the energy and the lysine a little bit on those diets to deal with that lactation reduction in feed intake?
So I got the first part of your question. You said that the capacity to cool them down during different times of the year. And then what was the second part? Sorry.
Oh, the second part was how much of an impact can you expect if you concentrate the diet with more energy and more lysine, for example? So let's say if average the feed intake in lactation is 5 kilos, then during the heat stress, it will get reduced to 4 kilos, and you adjust the diet to that. So how much of that can you cope with that
Yep.
without cooling them?
I think I understand. So basically you're asking, if you're not cooling them, what are dietary modifications that we can use to rescue the lactation? Is that what you're asking? Okay. I just have to base it on the research, right? So what we're seeing is that, again, that feed intake in the sow, at least from a research perspective, isn't rescuing lactation performance, at least all the way, right? We're seeing about a 50 to 60% rescue on that lactation performance just from the energy intake alone, and that those direct impacts of the heat stress are accounting for at least 40 to 50% of our decrease in lactation output, right? So, we can make that sow eat a ton of feed, like Dr. Schinkel was saying, at midnight or 1 a.m. or 2 a.m., but if she gets heat stress the next day, it doesn't seem to matter how much more energy we put into her. She's not partitioning it towards milk. She's putting it on her own back, not towards milk, right? Milk production is a homeoretic process, right? It's not really necessarily beneficial for that sow herself. She's altering her metabolic priorities to divert nutrients towards that mammary gland. When she's under a stress state, like I talked about, where they're prioritizing their own survival over productivity, the likelihood of her putting energy into a process that isn't going to benefit her is pretty low, right? And so we can rescue some of it with feed intake, but not all of it. So cooling her is really going to be a very effective strategy in combination with feed intake to try to get that back up to thermoneutral levels.
Okay, let's thank Dr. Johnson.